Hello, everybody. My name is Izzy Grossoff. My pronouns are they, she. And today I'm recording a tutorial that I gave at SIGMETRICS 2024 for the SIGMETRICS YouTube channel, for my YouTube channel, so people can see it even if they weren't there at SIGMETRICS or went to a different tutorial that day. Right, so today's tutorial is analyzing queues with Markovian arrivals and Markovian service. As I said, my name is Izzy Grossoff, and this was designed with my co-author and former advisor, Markovian. Now, as you know, throughout this tutorial, there are several Q&A opportunities. I'll ask a question. You should try and work through it. Feel free to pause the video to work through the problem, and then I'll show the answer on the slide shortly afterwards. All right, so let's get started. So the idea here, so before I get started, I just wanted to thank all my collaborators who made this research possible. So I've shown them here on the slide, lots of collaborations, lots of good times, and lots of work on. So the idea of this setting is queuing systems with fluctuating load. So the reason this is important is because the vast majority of queuing theory focuses on settings with independent and identically distributed inter-arrival times, likewise IID service. And what all this adds up to is a setting with fixed load, where, you know, if the system's stable, it's always just, you know, nothing complicated going on, at least from a load perspective. But a lot of real systems are quite different. So for instance, you might have correlated arrivals in practice. If you have a burst of arrivals, they'll be all correlated together. Correlated service, fluctuating load, it's overloaded sometimes and underloaded at other times. It gets complicated. So just some examples of what that might look like in practice. Maybe you're in a retail setting and there's a checkout line, and sometimes you have more cashiers on the lines and other times less. So sometimes you have people showing up faster and the queues are getting longer. Sometimes you know, more cashiers, it's shortening the queues. That's fluctuating load. Maybe it's a restaurant setting. So there's a dinner rush and lots of people are showing up. Other times, you know, it's 4 p.m., not too many people are coming through, fluctuating load. Maybe it's a healthcare setting, getting to something a little more important. It's an emergency room with things like congestion and time of day and time of week and a lot of other things like this. The load on healthcare fluctuate wildly. So that's another setting that this might look like, where this sort of concept might be important. Then we move to a more computing setting. So something like a data center, right? Sometimes, you know, there won't be a huge demand on your service. You'll have relatively low load. Other times it'll be higher or even peak load. And also, if you're trying to run your data center in a carbon efficient manner, maybe you have more capacity when the sun's shining and the wind's blowing. Maybe you guide load towards or away from your system when this happens. It's a fluctuating load system. Maybe it's a network setting, and you know you're sending some packets over Wi-Fi, and the environment is fluctuating as like the wind's blowing or there's objects moving around in the environment. Your service rate's going to fluctuate, so your load's going to fluctuate. And maybe you have more applications. You know, I by no means have heard of everything there is to know. But what I do know is this fluctuating load model shows up a ton in reality. So what are we going to do about it? How are we going to analyze these systems? How are we going to make a model that captures what's fundamentally going on here while still being tractable to theoretical analysis? So to do that, what I've been focusing on, and what I'm here to tell you about today, is a model called Markovian arrivals and Markovian service. So the core of it is a queuing system. We've got a single queue, some number of jobs in the queue, jobs are undifferentiated. But where the interesting part is with the arrival process and the service process. And both of these have continuous time markup chains with different states corresponding to different arrival rates to the system, and another continuous time markup chain with different service rates from the system. And if we zoom into this arrival chain, really what's going on behind the scenes is we have a bunch of different possible arrival rates, and the system will fluctuate between them according to the CTMC and thereby change over time. And something similar happens with the completion chain. And our goal in this talk is going to be a simple and explicit characterization of mean Q-ling. So we want to understand the performance of this system. We want to be able to do that no matter what the fluctuations of arrivals and service looks like, so you can really capture the full complexity of this system. So to give you an outline of the talk, so I've told you about this MAMS model. When it comes to analyzing its performance, the fundamental challenges will be illustrated by a simple instance of the model, which I call the two-level arrival system. So we'll go through trying to analyze that system, and then we'll come back to the full MAMS model. So specifically, I'm going to tell you about the drift method, which is going to be the key approach we use for analyzing the system. Then I'll tell you about this new concept we've come up with to allow us to apply the drift method to the MAMS system, which is called relative arrivals. And then I'll show you what results that allows us to prove for this two-level system. At this point, in SIGMETRICS at least, there is a break. Feel free to pause the video and come back. And then we're going to generalize to the full MAMS system after the break, and then talk about applications of this fluctuating load approach and generalizations we can come up with beyond even the full MAMS system. All right, so let's get started. So let me tell you about this simple MAMS system, the two-level arrival system. So here, we'll make the completions as simple as can be, just an exponential service rate. And for arrivals, we'll just have two arrival states, high intensity and low intensity. And the system will switch back and forth between those with two rates, alpha L moving from L to H, and alpha H moving from H back to L. And so behind the scenes, it means we've got our lambda H and our lambda L, and we'll switch between them. We'll stay in H for x of alpha H time, and L for x of alpha L time. And once again, our goal here is to characterize the mean Q-ling. So let me tell you about some prior work on this two-level arrival system and on the MAMS system more generally. So one category of efforts is what I would call computational methods. So this would be things like the generating function approach or matrix analytic methods. Now these are very good as far as they go. If you plug in specific parameters, you can chomp away at it and it'll output a computational result. But to get that result requires doing things like taking roots of relatively high degree polynomials, like in the generating function approach, or inverting pretty large matrices, like in the matrix analytic approach. And what this means is you're not theoretical insights, asymptotic results, sort of things you can draw lessons from via these methods. So they're good as far as they go, but they won't give you more than what they're good at. Then there's been some degree of symbolic results. One category of this is with a method called the M-step drift method. This is a heavy traffic result, and it's sort of semi-closed form where there's still an infinite summation, but there's a convergence result. It's by Mo and Magloire from 2020. You can think of M-step drift as basically, it's emerging from the drift method that we're using, but it's a much more complicated variant of it. And that's why they're only able to get this semi-closed form result. And it's sort of a more complicated and therefore less powerful technique. There are also some nice structural monotonicity and convexity results, like Gupta 2006 and Veslow, Harker, Bolter, and Scheller-Wolf from 2021. And these are great. They tell you as you vary certain parameters, and this work is specific to the two-level arrival system, as you vary certain parameters, does the behavior of the system increase or decrease or accelerate or decelerate? So it's very nice. That being said, it's not going to give you tight bounds. It's all this sort of qualitative information. And really, what I want here is a simple formula for mean Q-length, either an exact result or some nice tight bounds. And what do we have there? No prior results, open problem. But if you listen through this tutorial, and more specifically the first half of this tutorial, we will present relative arrivals and drift methods. So, and the reason there's a to-do floor in here, I didn't get a chance to update that, is there are some results by 2019 paper of Florin to, I don't know how to pronounce his last name, one of the organizers of SIGMETRICS this year. So some nice results there, different inspiration, different approach to ours, and more specific to two-level rival system. Our intent is really to get simple formula for mean Q-length. It's going to generalize the full MAMS system. But it's some very nice results and ones I didn't know about before giving this tutorial the first time. Okay, so we've got our goal, the simple and explicit characterization of mean Q-length for this system. So to get you thinking about how the system works, let me start by asking the first question. What fraction of the time does this system spend in the high arrival intensity state? Okay, so the arrivals are going off and doing their thing. They're doing their arrival chain, switching back and forth. What fraction of time are we in the high arrival intensity state? Think about that for a moment. Feel free to pause the video. So the other question I want you to think about is the arrival rate, lambda. So you know there's lambda h intensity in the high rate, lambda L arrival rate in the low intensity rate, and you've calculated the probabilities of high and low. So what's the overall long-term arrival rate to the system going to be? So think about both of those questions. And once you've thought about it a bit, or maybe pause and calculate out, or maybe calculate on the fly. So the fraction of the time the system is in the high intensity state is alpha L over alpha L plus alpha H. And that makes sense if the rate of moving from L to H is very low, we're not going to spend much time in the high intensity rate. And if it's very high, we'll spend all of our time in the high intensity rate. And PL is just the rest of the probability. And to calculate the arrival rate L, we just multiply these two by the conditional probability, the conditional rates, and we get this overall arrival rate. Okay, and we'll use that in the formulas we're going to develop going forward. All right, now the method we're going to use of analyzing mean Q-length is something called the drift method. I'm going to give you a bit of background. It's sort of a tutorial within a tutorial. I'll give you a background on the drift method. And if you understand that, that's how we'll analyze the mean Q-length in this MAMS system. So the way it works here is you choose a random variable V, any random variable you like. And the key idea is that the increases in the random variable V are going to match the decreases in the random variable V. So what does that look like? Here we'll look at the value of the random variable over time, and here's time. And sometimes it goes up, and sometimes it goes down, and it goes up some more and down some more. And the point is, all the ups match all the downs. They balance each other. From perspective, what we can say is, in stationarity, the expected increase is going to match the expected decrease when we average over the stationary distribution of the system. Okay, so that's the drift method. Now let's apply this to a real simple system, the MM1. So constant arrival rate, constant completion rate. This is one of the first things that people see when they're looking at a queuing system. But if you can understand how to apply the drift method here, that'll put you on the right framework to apply it to more complicated situations. So we're going to use the random variable Q squared. So our V from the last slide is going to be the square of the Q length in this slide. We're going to use the drift method to calculate the mean Q length. Okay. So here's what the Q length at time t squared might look like. Maybe it starts off at 0, up to 1, down to 1, or up to 1, down to 0, to 1, to 4, to 9, etc., etc., etc. And we've got our increases and our decreases. Now, just move some things around. Okay. Now, let's suppose that at a given point in time, at some particular time t, the Q length is a little q. How could, what are the ways in which Q squared can change? What are the rates of those changes? What amounts of change will occur? So the ways that the Q length can increase are by arrivals happen. And the ways that it can decrease are by completions happen. So what I want you to do is think about what rate do arrivals happen and what's the change in Q squared when they happen? And what rates do completions happen? And what's the change in Q squared when they happen? So again, feel free to pause the video, take a bit of a think about this. So the rate of arrivals happening, that's just lambda. That's an MM1 for you. And the amount that Q squared changes is by 2Q plus 1, right? Because it goes from Q squared to parentheses Q plus 1 and parentheses squared, which is an increase of 2Q plus 1. Okay, so that's the rate and that's the amount of change. And for completions, it's something very similar with a little added complexity. So at a rate of mu, the change is down by negative 2Q plus 1. So it goes from Q squared to paren Q minus 1 and paren squared. Except that if the Q length is already 0, then mu can't change. So pretty simple, pretty straightforward. So now what are we going to do with this? Well, we know the rates of change at a particular Q length. Now we're going to look in stationarity. So what is the expected increase in Q squared at a stationary moment in time? What is the expected decrease at a stationary moment in time? So if we work through, so here's another question for you. You can work through it. The increase we end up getting is just lambda times twice the mean Q length plus 1. Before it was the specific Q, now it's the mean Q length. So the decrease is mu times negative 2e of Q, and then instead of plus 1 here, we actually have plus Q length plus the probability that the Q length is greater than 0, and that's to correct for that edge condition. And since we know the probability that Q length is greater than 0 is just lambda over mu, we can multiply it all out and simplify it like this. So now we know that the increases have to balance the decreases. So these two terms here are going to sum to 0. And because they sum to 0, we're going to be able to calculate the mean Q length. So again, take a pause and try and do that. So once you've calculated out, the result is that the mean Q length is just lambda over mu minus lambda. Or if we divide through by mu, rho over 1 minus rho. This is a very famous result. A lot of you will have seen it before in your queuing textbooks or whatever. But, we found a new way to prove it that maybe you hadn't seen. All right, so this is the drift. So here's our rainbow ball of results. We've proven what we wanted to prove. So let's just formalize this drift method a little bit. Instead of just talking about a random variable, it's often helpful to think about a test function. Now, test function is just a function that maps states of a system to real values. So in this case, we use the function that maps Q length to the Q length squared, okay? And to formalize increases and decreases, we'll use something called the instantaneous generator. So that's defined as follows. The instantaneous generator of some particular function is just the change in that value of the function from time 0 to time t in expectation divided by t, limit to 0. So this is basically the stochastic equivalent of a derivative. It's how much a function changes, divided out by 1 over t to get it to balance, limit t goes to 0, and we're just stuck in expectation. But when it comes to countable state systems, like we're looking at here, countable state and continuous time Markov chains, we don't need to go through this full definition. We can just look at the rate of change, like the rate of leaving some state, times the amount of change that movement would cause in whatever our test function is. And that's what we're going to be using for the rest of this talk. And we can also formalize the key drift theorem. The drift theorem says, if I have a test function whose mean is finite, then its stationary drift is 0. So the mean of the drift of f in stationarity is just 0. All right, so that's the drift method you see in the MM1, you see in the formal description. Now it's time to apply it to our two-level arrival system. So the first attempt, we're going to use a real straightforward test function. Let's just use the same random variables before Q squared. Now, remember, there are 4 ingredients to drift. There's the rate of arrivals, the change in the test function due to an arrival, the rate of completions, and the change in the test function due to completions. So for your next question, of these 4 components, rate, change, other rate, other change, which one changed when we went from the MM1 to the two-level arrival system? Which one's different than it used to? So give that a bit of a think. Yeah, so the rate of arrivals is now state. So where before the rate of arrivals was fixed, it now depends on whether we're in the high arrival state or the low arrival state. All right, so let's give this a name. Let y of t equals little y be the arrival state, and it'll be big Y in stationarity. So if we're in a particular state with Q length Q and arrival state H, the drift due to arrivals will just be lambda H 2Q plus 1. Before there was no sub H. And similarly, if it's an L, lambda L 2Q plus 1. So what's the expected drift due to arrivals going to be in stationarity? What does the expectation of all this look like? You can give that a bit of a think. So what we get is 2 times the expected product of lambda of whatever the arrival rate in stationarity is, lambda y times q plus the overall arrival rate. And this is not so good because we now don't know anything about the mean Q length, the thing we wanted to look at. We only know the arrival rate weighted Q length, and that's not nearly as useful. So the results ball is not happy. And when we try to use, our key drift theorem, all it tells us is a relationship between the arrival rate weighted Q length and the mean Q length coming from the completions term. And there's no way to extract a mean Q length result out of this combination. So our results ball is still not happy. So the conclusion here is that the Q length squared, that random variable, that test function, it doesn't work for the two-level system. We're going to need to find something else. The key idea of the drift method is you've got to find the right random variable or the right test function for your particular system. Q length squared was right for the MM1. It's not right here. What we need here is a way to smooth out the arrival rates, to sort of dampen the impact of switching back and forth here, so that our term is not arrival rate weighted anymore, so that we get a E of Q drift term, both coming from arrivals and coming from completions. And so they can match up and we can analyze mean Q length at the end of the day. So to make this happen, we came up with a completely new idea and something called relative arrivals. Let me show you how it's going to work. So first, let me define A sub y of t to be the number of arrivals up to time t with the system initialized at time 0 in arrival state y. And we can define relative arrivals. What we do is we take the expected number of arrivals up to time t starting in state y and subtract out the long-term arrival rate lambda t. Then we take this difference, which is going to be some number of jobs, and we take its limit as time goes to infinity. And so it tells us, because you started in this state, you're this many jobs ahead. And that number of jobs ahead is delta y. This is a little hard to understand just math-wise, so let's look at it visually. On the vertical axis, we're going to have expected arrivals. On the horizontal axis, time. And the setting will be this. So lambda t, that's just a straight line. That's our long-term arrival rate, which here was just 0.5 jobs per second. And if we start in the high arrival rate, well, jobs are initially arriving at 2 jobs a second from the beginning. So as a result, the arrival rate is going to initially be much higher. And then as time goes on, maybe we switch to the low rate, we switch back to high. Things are going to even out until in the long term, we match that. We have the same slope as the long-term arrival rate. But because of starting in this particular state, we've got some transient impact from our initial state, which leaves us with this additive difference in number of jobs. Similarly, if we start in the low arrival state, we'll be below that curve and we'll have a negative additive difference. We call the difference here delta. So delta H is the difference between long-term rate and expectation AH of t, and delta L is difference down to expectation AL of t. So that's relative arrivals. All right. Now, you might look at this and be like, okay, how are you ever going to calculate this? Well, you could try to calculate the exact function expectation AY of t. I actually did that to generate this plot originally, but it's not a very effective way of calculating these limiting values. Instead, an easier way to calculate them comes from a connection with Markov decision process theory. If you haven't heard about that before, don't worry, you won't need, it's not prerequisite material, but it does make it make more sense for people who've seen it. Basically, we can think of delta y as the relative value of a Markov reward process whose reward is the instantaneous arrival rate of the system, lambda sub y. And there's a standard way for calculating relative value, which is called Poisson's equation. So in this particular situation, the way that works is to say, if you want to calculate delta H, you split up time into 2 time periods. First, before the next arrival process switch happens, and then after the next arrival process switch happens. So before it happens, this expected AY of t, that's going to be going up at rate lambda h. But then we subtract out this lambda t for a difference of lambda h minus lambda per second. And how long is it until we switch? It is 1 over alpha h time until we transition to state L. So we've got this much accruing until we switch to state L, and then just delta L from that point onward. Another useful fact is that the mean relative arrivals in stationarity is just 0. And that's because the expected number of arrivals in stationarity is just a constant lambda jobs per second. There's none of this variation that comes from being outside of stationarity. So this one is 0, and this basically gives us 2 equations for delta H and delta L, and that's enough to solve for their values. Now, I'm not going to ask you to do that here, but one gets is that delta L is lambda minus lambda H over this, and delta H looks very similar, but with all the H's and L's flipped around. Okay, so we've calculated relative arrivals. Now, what are we going to do with these? Well, we're going to take their drift. After all, it's called the drift method. I hope we'd be taking a lot of drifts. So let's ask the question, what is the drift of this relative arrival? What's the drift of delta y? And remember, this is that relationship between delta h and delta L. So to do this, we're going to break it up into 4 questions. First, what would make y change? Let's remind ourselves what this y thing is. So y is the arrival state, so this changes when we change between h and L. At what rate does y change? Well, it changes at rate alpha y. It might be by how much does delta y change when it does? This is a little subtle because this is on the wrong side of the equation, but it's going to be lambda minus lambda y divided by alpha y. If you imagine moving this to the other side, you'll get the change. Okay, so let's put it all together. We've got the rate, we've got the amount of change. So what's the drift of delta y? Well, it's just lambda minus lambda y. We just multiplied alpha y by this change. And actually, and this is great. This is actually just what we want because, and we're going to see exactly why it's so useful in just a moment. Actually, you can think of delta y as just being the test function with drift lambda minus lambda y. That's really what we end up using it for, is that it's got this drift. So that's the inspiration for delta y. That's actually how we derived it in the first place. Okay. So now we're ready to apply the drift method to our 2-level orbital system. So first, what's the drift of our Q length? Well, it goes up at rate lambda y, like we said before, and down at rate mu, like always, and then this edge condition when the Q length is 0. And this is not great. The fact that we have this lambda y in here is the reason why we have that arrival rate dependent, the arrival rate weighted Q length in our result before. So we want to get rid of this lambda y before we can really use the drift. And this relative arrivals function is perfectly suited to do that. It's just lambda minus lambda y. So it's got a lambda y ready to cancel out this thing. And so if we add them together, the Q length plus delta y, it's got that perfect drift that we wanted. It's got that drift of lambda minus mu, again with the edge condition. So this looks just like what the drift of the Q length was in our MM1 system. Constant arrival rate, constant completion rate. So this is the perfect proxy for the Q length. And so now we're ready. And so a key idea of the drift method is that if we can get a constant drift function, like this one, where other than this edge case, the Q length doesn't affect the drift here. If we can get constant drift, we can get linear drift. And if we can get linear drift, like linear as a function of the Q length, we can get the mean Q length. So to get our linear drift, I've said magic test function here, but really it comes from just squaring our constant drift and then getting rid of a term we're not going to use. So we have the Q length squared plus this compensation term of 2Q and the relative arrivals. So if we go and calculate the drift of this function, it just involves calculating the drift of the Q length squared, like we did earlier, twice the Q length times the drift of delta y, and twice the relative arrivals times the drift of Q. So you've got all the information you need to calculate it. I'm not going to ask you to do that because it's a little obnoxious. What you end up getting is this following expression. And I know it looks kind of ugly, but let's just separate it into two pieces. This part over here, this depends on the Q length, and it depends linearly on the Q length and not at all on the arrival state y. It's just 2Q and lambda minus mu. And then everything else over here is bounded, right? It depends on y, it depends on whether the Q length is 0, but it doesn't depend on the absolute value of the Q length. And so there's only like 4 values this can possibly take. It's certainly not growing arbitrarily. So as the Q length gets long, this linear term is the one that's going to dominate. And this one is really simple and we can understand it. So this is perfect for trying to analyze the system. So we've got our drift function. Now let's apply our key theorem, which says that in stationarity, this drift is going to be 0. So we take this and look at in stationarity and say it's 0. And that tells us the following. We've got our linear term, which has become a mean Q length term. We've got a bounded term, which has a couple different pieces. It's got a term here, which is just an expectation of something depending on the arrival process. And since we know the stationary distribution of the arrival process, we can calculate it. It's got this term over here, which is going to be a little more annoying, and we'll talk through that as we go. So the result we have here is that the mean Q length in the 2-level system is just rho over 1 minus rho, so the same expression we saw for the MM1, times this extra factor, the mean relative arrivals weighted by the arrival rate divided by lambda and plus 1. So this term over here is the term that's going to dominate, for instance, as load goes to 1. This is the big important term. And this quantity here, this expectation, we can calculate exactly with no trouble at all. And then we've got this extra term over here, which is the expected relative arrivals conditioned on the Q length is 0. And that's a little more complicated to understand. Let's take a look into it on the next slide. So we've got our theorem here. This leading term here, we just calculate this explicitly, and it's actually a very nice formula. It depends on the high intensity, low intensity, and long-term arrival rates. And so this term over here, the heavy traffic behavior, we can understand exactly. Now, if we expand out this expectation over here, what we get is that basically we can understand everything except for this one important term, the probability that we're in the high arrival state while the Q length is empty. And that term, we don't know it exactly, but we can prove some bounds. And from those bounds, we'll directly get mean Q length bounds, since we can calculate everything else in this formula. And even if we just plug in the bounds that this probability is between 0 and 1, we already get some pretty nice results in a wide variety of settings. And if we do a little bit of extra effort, which we do in this paper, analysis of Markovian arrivals and service with application intermittent overload, we get some very nice bounds on mean Q. And you can take a look at this paper, it's on our. All right, so we've got some bounds. I said they were good. Let's see what that looks like in simulation. So here I'm going to show you the mean Q length as a function of load in the following setting. So we've got our high arrival intensity, which will be varying as a function of this load. Low arrival intensity will be 1/10 of that, and the system spends most of its time in the low intensity state, and the service rate is 1. And here are 3 different curves for 3 different settings. This first setting, the blue one, is very slow switching. So we spend a lot of time in overload and then a lot of time with low intensity and back and forth. And so our mean Q length, as you can see, it's going up, and it's very well predicted by our bounds how it's going to evolve. Here in orange, we've got a medium arrival intensity, and our bounds are again very good. And in green, we've got sorry, I said medium arrival intensity, I meant medium switching rate, and our bounds are pretty good. And in green, our bounds are the best of all. That's very fast switching. So the point here is we have very nice bounds, and they correctly predict what the behavior of these systems is going to be to within, a job or a fraction of a job. All right. So let me just review some of the key ideas of this part of the talk. So the key idea was we wanted to design a random variable or test function to have just the right drift for what we wanted to analyze the performance of. And the key to making that happen was to separate out the Q length dependent part of the drift from the arrival state dependent part. We did that with this particular test function, which we developed by finding just the right delta to cancel things out. And that gave us a linear term over here, dependent on the Q length, and a bounded term over here that didn't care about the Q length beyond whether it's 0 or not. And this idea in general, this designing a test function, separating out Q and Y, it's a very widely applicable idea, far beyond anything I'll talk about in this tutorial. All right, so it's time for a break. Feel free to pause the video, go away for 5 minutes, come back. Listening to this whole thing in one setting might be a bit much. And here's the system and the result that we saw so far, just to give you something to talk about. All right, so let's return. So just to come back to our outline. So we looked at the simple MEMS system, and we tightly bounded its Q length using the drift method and relative arrivals. Now, after the break, what we're going to do is generalize to the full MEMS. We're going to look into a variety of applications. First, the basic fluctuating load setting. Then we're going to look at a multi-server job setting, and the generalizations we'll need to capture that. And then we're going to look at networks with abandonment. So this will include a tandem queuing system with abandonment and a quantum switching network. All right, so general Markovian arrivals, Markovian service. So that we've got some general finite state CTMC over here and another one over here. And behind those are some fluctuating arrival completion. And again, we're trying for simple and explicit characterization of mean Q length. So first, we're going to need to generalize these concepts of relative arrivals that was so important before, and introduce a new concept called relative completions. So for relative arrivals, we're going to use the same definition we used before, just this difference in between expected arrivals up to time t starting in YA and the long-term arrival rate lambda. And for relative completions, we'll just copy the same idea, expected completions up to time t starting in YC minus the long-term rate mu t. So just to draw some pictures of that, we've got our long-term rate, and our arrival process might go around for a while and settle out at some particular offset, and that's our delta A. And a similar idea for completions, long-term rate, and settle out, and that's our delta C. So nothing's changed here. And when it comes to drift, so Q length has a drift, a state-dependent arrival rate drift, a state-dependent arrival rate shows up in the drift, a state-dependent completion rate shows up in the drift, and our edge case has a slightly different form than before. Yes. Now, relative arrivals, as always, lambda minus instantaneous arrival rate, that can cancel out the lambda YA over here. And that's the same drift as before. And relative completions, just the same idea. And this mu minus mu YC, that can cancel out this and give us a constant drift again. And here's what that constant drift looks like. We just take our Q length, add our delta A, subtract our delta C, and we've got a constant drift up to the edge case. And so the key idea here is, remember, if we can get constant drift, we can get linear drift. If we can get linear drift, we can get mean Q length. So we build our magic test function, self-random variable. Once again, it looks just like before, but with a subtracting off 2Q delta C. And we can calculate our drift, and it once again has a Q length, a portion that's linear in the Q length, a 2Q lambda minus mu, just like before, and the term that's bounded and only dependent on YA, YC, and whether the Q length is 0. All right, so we've got our drift, and from drift comes mean Q length. And our mean Q length result is pretty nice. We've got this one term that cares about the arrival rate weighted delta A, one that cares about the completion rate weighted delta C, and this extra plus rho here at the end. And so this is our main term, the one that's going to matter in heavy traffic as load approaches capacity. And then we have an extra term. Now this E sub U over here, that's an expectation over moments of unused service. So it's saying when the service process wants to complete a job, but there's nothing in the system to complete, what are the values of delta A and delta C in those moments in time? And that's the sort of extra term we don't completely understand. But even just from the basic bound that delta A and delta C are between the minimum and maximum values of delta, that's already going to give us good bounds. Because remember, there's only a finite number of states of our CTMC, so delta A and delta C aren't going to be too bad. Okay, so let me just give you another moment to look at this. This is our mean Q length result for the full MANS system, tight and heavy traffic, and really not too bad outside of heavy traffic. So we've done it. We've got our simple and explicit bounds on mean Q length. Wonderful. So we've looked at the full MANS system. Now let's talk about some applications. So first, let's look at fluctuating load setting. Let's imagine you're operating some kind of data center. So we want to plug in our data center. What's a good model for what our arrival process might look like and for our completion process? Maybe for arrivals, we've got 4 different intensities of, maybe there's normal arrival rate, maybe there's off hours where we have less, peak load where we have more, and some rare event like a big sale or a ton of interest in whatever we're operating, that's going to be really intense load. So we could have a Markov chain that looks like this. You go from low to normal to peak to super intense, and maybe back down. So maybe that's what arrivals look like, and there's some rates on all these. And for completions, maybe we've got full operation, things are going well. We've got something's down for maintenance, and we've got there's an outage. So maybe things go back and forth between full operation and maintenance normally, and occasionally go to an outage, and eventually return back to operation. So we've now modeled our arrival and completions process, and the MAMS model is going to give us a performance characterization based on the relative arrivals and relative completions of these two systems. And those are just, numbers that we can calculate for each of the states in the system and get a mean Q length result. Okay, now let's turn to a bit of a more exciting application, something with a bit more theoretical novelty. So here is something I call the multi-server job model. The way it works is we've got jobs that require different numbers of queues. So this job needs different numbers of servers. This job needs 2 servers. This job needs 1 server, and different numbers for all the jobs in our system. We're going to run them in strict first come, first served order, so nobody feels like we're being unfair or anything like that. So this 2 server job over here, it wants to be in service, but there's only one server available, so it's going to have to wait. And this one server job, we're not going to let it jump ahead because, we want things to wait their turn so the two server job doesn't get even further delayed than it already is. And we'll think of a Poisson of lambda arrival process. Now, job here has a duration and a server need, and I'll write the server need in that little box there. And we're thinking of these being sampled by ID from some joint distribution with face type job durations. But just to make it simple to illustrate in this talk, let's think of a two-server system. So just two servers, jobs need either one or two servers, and we'll think of x with mu1 as a duration for the one server jobs, and x with mu2 for the two server, just to keep things simple for the purpose of illustrations. And again, our goal is to characterize mean queue length. So the thing to note here is we have service rate fluctuations, right? At this moment in time, only one server is active. So jobs are only completing at rate mu1. But they could both be active. They could be active with, two server job or two one server jobs. Now notice, this is different than the service rate fluctuations we saw in the previous fluctuating load example. This is an internal cause of service rate fluctuations, not some external cause like an outage. But our key idea for looking at the system is we can use Markovian arrivals and Markovian service anyway. Now, to make that possible, let's think about this question. What service rates are possible in this system? And specifically, what service rates are possible when there's lots of jobs in the system? So I don't care about like the service rate could be 0 if the system is empty. If I have lots of jobs in the queue, how fast could I be completing jobs? So take a think about that for a moment. Yeah, so we could have one single server job in the system, then we'd have a mu1 completion rate. We could have two, then we'd have a 2 mu1, or we could have a two server job and this we'd have a completion rate of mu2. So if we draw that out, we would get an MAMS system that looks a bit like this. If we had a single one server job in service and it completes, we're definitely going to move to having a two server job in service after that, as you can see here. To have a one server job in service, we must have a two server job waiting behind it, blocking out that other server. Similarly, if we have two single server jobs and one completes, we might have another one empty, or we might go down to a single one server job in service. We're not going to jump directly to having a two server job in service. And notice here, this is a slightly different variant of the MAMS system. This is the rate at which a job completes, which both completes a job and moves us to the next state. It's not like automatically stay in the same state and have a separate switching rate, which is what we saw in the previous system. So just a slightly different variant that's helpful for modeling this multi-server job system. And don't worry, the same analysis works for both of them. Okay, so let's look at these two systems. We've got our multi-server job system and our MAMS system with a completion rate process that was modeled after this system. So are these two systems identical? Like, are they always going to have the same mean queue length and all that? Well, they're almost identical. In particular, we could delay sampling the job type until a job reached service or is eligible to service. And then they start looking really similar. So we just have a bunch of identical jobs in both systems, at least until things hit service. But there's a more important difference, which is in this system, the system can empty completely. This system, even if the system empties completely, you'll still be in one of these service rates. In this system, if the system empties completely, it's a fundamentally different state of the system. Or if you have one job in the system, it can also be there. But once you have two or more jobs in this system, they really are indistinguishable in a certain way we can make form. So once you have two or more jobs in the systems are identical. So we call this a near MAMS system because it's got some finite threshold after which it is indistinguishable from an MAMS system. And we actually have a theorem that applies to any near MAMS system. It tells us that the mean queue length in this near MAMS system is the same as the mean queue length in this exact MAMS system, with the equivalent service process, plus some constant number of jobs where that constant number does not increase or does not diverge as a function of the load growth. It depends on all sorts of things about the system, but it's not getting dramatically bigger as the queue length is getting longer with high load. And this was all proven in a paper called the Reset and Mark Techniques with Applications to Multi-Server Job Analysis from Performance 20. So this is one way you can use MAMS ideas, even if your system isn't exactly an MAMS system, for analyzing these sort of multi-server fluctuating service rate systems. Another application that I want to talk to you about is a tandem queue with what I call hybrid abandonment. So the idea here is, imagine you're in a coffee shop, okay? So first, customers are going to queue up in order to order their drinks and pay. And they might abandon while they're here, meaning they might just give up, leave the coffee shop, go somewhere else if this queue is taking too long. Then after they've ordered and paid, they're going to queue again to pick up their drinks. And nobody's going to abandon from there because they've already paid for the drinks. They're not going somewhere else anymore. And so our question is, what's the mean queue length in the system? Now this queue is never going to get too long because people are abandoning them. So if things are going poorly, this queue is the one that's going to get really severe. So to analyze the mean queue length of this system, our idea is to think of the first queue as a Markovian arrival process. Okay? So, basically this queue is controlling the arrival rate to this queue. So we can think of it just like before we had our two-level arrival process. Now we've got an abandonment queue arrival process. Completions from here are the arrivals from here. So what I'd like you to do is draw a Markov chain corresponding to the arrival rates from here to the second queue. What different states are possible in the system, and what completion rates and thus arrival rates of the second queue do they imply? I'll give you a chance to think about that for a moment. All right, so here we go. The way it works is if this first queue is empty, then the instantaneous arrival rate to the second queue is 0. But once we get a job in here, or more jobs, the instantaneous arrival rate is just going to be the completion rate of the first queue. So yes, it's an infinite state Markov chain, but there's only 2 arrival intensities, 0 or mu first. So we call this an infinite MAMS system. But the nice thing is there's some uniform positive recurrence going. So even as the arrival rate is approaching the capacity of the system, that just means the second queue is getting long. The first one is still, return. Is still a recurrent Markov chain with rapid recurrence happening. It's still returning to the empty state frequently. And so we can still define the relative arrival function of each of these states. And it'll be a different value here, and here, and here, and at every single state. And we can still get the same mean queue length, which looks like this. The mean queue length of the tandem queue is just the same formula as before. Now it's a little more work to bound this delta y given q equals 0. Before we depended on the fact that relative arrivals had only finitely many possible values. Here there are infinitely many possible values, but it's something we can make to work. So we can analyze this tandem queue with abandonment on one side, but not on the other side, using this infinite MAMS concept. All right, so one more application for you, a quantum switching. So let me tell you a bit about a model of a quantum switching network. So the idea here is, and don't worry if you haven't seen quantum stuff before, I'll tell you everything you need to know. It's not so complicated. So this switch is a device that's going to generate something called entangled qubit pairs. And the thing you can do with an entangled qubit pair is you can send one half of this entangled pair to the other side. So now these two are sharing this entangled pair. Maybe this is a lab over here, and this is a switch. And this lab over here would like to share an entangled pair with this lab over here. Right now, only has this short distance entanglement. So these switches are going to generate more and more entangled pairs, stretching all the way across like this, but it's still 3 separate pairs. We want one pair with a half on this side and a half on this side. And the other thing a switch can do is combine 2 entangled pairs in order to make one longer distance pair. So we went from 2 short pairs to 1 long pair, and then we're going to take this longer pair and make a really long pair. And that's what we wanted at the end of the day. We now have an entanglement between maybe our lab over here and the other lab over there. And this model, I didn't come up with it. This is specified in matching queues with abandonment in quantum switches, stability and throughput analysis by Zubeldia, Procured, and Civitation. Martin, Procured, and Civitation. Okay, so how are we going to analyze this? Well, let's draw this from the perspective of a switch. Okay, this is a global perspective. Let's draw it from the perspective of one of these switches. So we've got our switch sitting in the middle here. And over here, it's generating qubit pairs. It says, okay, I've made a qubit. I've sent one half over there, and I'm holding onto the other half. And inside the switch, there's a bunch of little cues saying, here's my half of a pair. And notice these all have an abandonment arrow, and that's because qubits aren't the most stable. They decohere pretty easily, which means they like bump into the wall or they get a little heat in there and they don't do their job anymore. So these are the qubits we have left. Now, on the other side, we've got requests for longer distance entanglement. So maybe somebody's asked for an entanglement between A and B, and those are those Q, and somebody's asked for a long distance between B and C, and that's over here. So right now, the switch can't serve any of these requests, but if it manages to generate another qubit pair with B, it can now serve a request. So it'll take the request, it'll combine A and B, and boom, those leave the system. We've served a request. So you notice here, this also has the behavior of sort of a hybrid abandonment, non-abandoning system, right? The qubits are abandoning, the requests just wait until they finally get served. And what we want is a simple explicit characterization of mean Q length, just like for all these systems. Now, what we're going to start with is just talking about the simplest quantum switch you can hope for, just 2 kinds of qubits and 1 kind of entanglement of requests, not because you necessarily build the system this way, but just to keep it simple. So our idea here is just like before we thought of those arrivals as we thought of the first queue in the tandem queuing system as a arrival rate modulation process. Here we're thinking of the qubits as a service rate modulation process. Same sort of approach, but so we've got that uniform positive recurrence we need, right? Because of those abandonments, these queues are never going to get too long. The requests are the only things that could get backed up. But because it's on the service side of the system and not the arrival side of the system, there is like alternative behavior when there's no request in the system, because we can build up both kinds of qubits in our system. And so this is actually a near MAMS system. So it's an infinite near MAMS, but we're pretty sure we can still use these combined techniques to characterize mean Q. And this is the final, most powerful technique of this sort of framework, at least that we've developed, at least that I'm going to talk about today. So that's how you could use MAMS to analyze the system, at least, if you get that generalization work. So some future directions to potentially take things. One thing I'm interested in, so this talk was all about mean Q length, but the tail of Q length is also very interesting. So maybe we could analyze the transform of Q length, e to the negative SQ for a variety of values S, or maybe the heavy traffic scale mean Q length, e to the negative S, 1 minus rho times the Q length. Another thing I'm interested in is what I call MAMS work. So the idea here is jobs would have sizes, and instead of modulating the job completion rate, we modulate the work completion rate, and then jobs would finish once all their work is done. And at the MAMA workshop at SIGMETRICS, which was a week ago today. There are also two papers, one that I presented, one that I'm a co-author on, that talked about using MAMS and drift concepts for scheduling ideas. So those were bounds on MGK scheduling at a moderate load, which I presented, and simple policies for multi-resource job scheduling, which Zhongray Chen, who's a PhD student at UNC, presented. And of course, I just know about the applications that I've already worked on. Your application, your model, your setting, these are all future directions of interest. So to wrap things up, we saw today the Markovian arrivals Markovian service system. We saw the drift method. We saw this new idea called relative arrivals and relative completions. And we put it all together to get a simple and explicit and tight characterization of mean queue length, both for the two-level system and for our general system. And we saw some applications, fluctuating load system, multi-server jobs, random queues with abandonment, and a quantum switching. All right, so that's all I've got for you today. Thank you for watching this video. Feel free to reach out if you want to discuss further. And thanks for watching.